I will talk about some small question I started recently, but I couldn't finish completely. There are some results. The problem is connected with some inequality, Hinchin's inequality. So it is the inequality was proved exactly 1 century ago in 1923, and after that it became very important tool in many fields. For example, in probability theory and harmonic analysis. This is the proving impact of this inequality is very easy combinatorics, but after that, so the inequality is this. We have Rademacher functions. Rademacher functions are in probabilistic way. You can say function random variables which equally take plus and minus 1 in equal measures. So the inequality says that if you take any sum of linear combination, you have this inequality. Here is square root p is very important part of this inequality, and first important application of this inequality was done immediately after 1 year. Hinchin he proved a well-known iterated law of iterated logarithm. I just mentioned that before that partial results was proved by Hausdorff. Many famous mathematicians was involved in this problem, and so let me see what can it give these inequalities. In general, if you have some function which has which LP norm has this growth, then you can get some super exponential inequalities like this. So in fact, all these inequalities are equivalent if you equivalent up to constant. But when we are seeking sharp constant in one of these inequalities, then you cannot get from one to the other one. So if you consider these inequalities in some situation for seeking exact constants like C or here, then you have to prove all this separately. So there are some different directions of the generalization of this Hinchin's inequality. You can see here some for independent random variables, for martingales, for multiplicative systems, Rademacher chaos. All these are some different directions of these generalizations. So here you can see the inequality. In fact, there are some other lower bound, or also there is some inequalities like this, and it is known some sharp constant here are these constants. So that means for any this AP and BP are sharp in these inequalities for all kind of these sums. The proof, so the history of this sharp constant, it has a long history. First, Hinchin proved this, found the exact AP for even P for greater than 4. Then Stechkin proved this is sharp for this P. Then Young proved for P greater than 3, and Sharek, solving some problem of Litwood, proved that B1 is equal 1 over square root 2. And finally, Hagerab in 1982 introduced a new method which allowed to get all kind of open parts of this inequality. And I would say the proof of Hagerab's method was a very deep method. The paper is about 50 pages long paper. So we are going to consider the best constant question for the martingales. Martingales, we have some probability space, and consider discrete filtration. That means we have some sigma algebras, monotonic sequence of sigma algebras, and if we consider discrete situation, then each Fn is generated by finite or countable family Dn, which is partitions of the X. And if you, in fact, we will suppose D0 is consists of one set. It is the whole space X, and if you take one element from Dn, then it can be written as union of few elements of Dn plus 1. And I will define the martingale difference. Usually, martingale difference are defined by first martingale, then difference of these martingales. But to be short, I will just define the martingale difference immediately. So, what does it mean? So, if you have, let me write dk is a we can all this consider on 0, 1. There is no any. So if dk is this, so it is piecewise step function like this, and dk plus 1 is I would like to write this condition. What is this? So dk is this. So dk plus 1. Here is some function which has zero integral on each these intervals of the previous decay. So this is the definition of martingale difference. When usually these intervals are called, these small intervals are called the children of this one. Children of this one. So when this part, when each element has two equal children, then we say this is a dyadic martingale difference. It is the case when, in this case, we will exactly get the Haar martingale. So Haar functions are very well-known functions in harmonic analysis, and those are very interesting properties. So when each element has two equal children, then we get the Haar martingale. And when and Rademacher functions are most simplest case case of martingale differences. We consider the following two square functions. The second one is the classical square function. For the first one, we have here we have, so you take the L infinity norm and multiply by the indicator function. It is easy to observe that there is some inequality, because we have in this case one can easily check that there is inequality. But in case of in case of Haar or Rademacher-Martingals, we have equality, and in case of Rademacher functions, those are just equal to the sum which we have in the Khinchin type inequality. So there are. I just want to show some couple of examples concerning to this situation. In fact, here we have some super exponential inequality, because here lambda square. This is well known Azuma-Hofting inequality and Chang-Wilson-Wolff inequality, where first authors use this square function. By the way, this non-classical square function was defined in Chang-Wilson-Wolff paper. This inequality has many different applications in very different situations, and I also have several papers where this inequality plays a significant role. I'm not going to talk about these applications. I just want to consider the So, and in the last recent paper of Ivanishvili Trail, they prove this inequality, but here considering not general martingale differences, but martingale differences, which in which the filtration is homogeneous. That means if you take some v from d k minus 1, then its children cannot be too small. So in this case, they prove this inequality, but here f is the classical square function. And also in the paper, they show that here they cannot drop the condition of homogeneity for martingale for the filtration. So the problem we consider is this. So we have some general martingale difference. We want to we are seeking the best constant that can be here. So the problem can be considered in two ways. You can fix n, then C will depend on n. Also, you can consider his with a free n, then C can here supposed to be some absolute constant. So usually this inequality for some C follows from the results above. Even we can here take C to be square root. The rate of this C is square root p. But we are seeking for the best constant. That is important part of this. We denote these constants by Pn. It is easy to see that this is monotonic with respect to n. And when you take the limit, AP will just give us the sharp constant here for free n. So you consider here all kind of sums, and it is so when of course here you can consider only Haar martingales or Rademacher martingales. Then the constant probably will be different. So we denote this constant by correspondingly by writing Haar or Rademacher. If you consider here only Haar sums or Rademacher sums. Clearly, we have this relation between this constant, but it turns out, in some cases, all these are equal. I just want to mention that according to the sharp constant estimate, you saw above, Rademacher. In the case of Rademacher functions, you have it is known this equality. So which is equivalent to this inequality we saw above. But in case of Haar or general martingale differences, so we have to do something. Also, Komarovsky in 1988 proved that for fixed n, for the Rademacher, again for the Rademacher functions, this constant is equal to this value, and that means the best, the maximum, if you take any Rademacher sum, LP norm, Rademacher sum with the L2 norm equal 1, then the maximum LP norm will get when the coefficients are equal. So so this is proved for p greater than 3, and I will okay. So there were some previous papers where and Komarovsky used some inequalities in these papers. Also, some review of these questions. One can find in these two in review paper or Peshkir Shiryaev and Sergei Yastashkin's book, new book. And so what we proved, which is not published yet, you can see it in the arXiv. So we proved that in p, if p is greater than 2, then you can, the constant for general martingale differences are the same as for the Haar case. In case of p greater than 3, you can prove more that AP is equal to the Rademacher constant, which is known to be this according to the Komarovsky results. So what does it give? What do these theorems give? So we just reduced the general problem to the case of Rademacher function in p greater than 3, and for general p we have in this general question you can consider only Haar functions, and so these are corollaries. So if you have this is the constant. So if you fix n, so this inequality is sharp in the sense that if you take here any martingale difference sequence, you have this inequality, and this is constant depending. This is the APN constant. So this is the sharp constant, and also if you consider the because this constant according to the central limit theorem, this constant tends to the this value. By the way, I didn't say the gamma is the just a gamma function. It is well known this LP norms tends to the this, and so as from this relation immediately follows the sharp estimate this with this constant, which is the same constant as we had in the Rademacher case. So this is proved for p is greater than 3. And in the case of Haar functions is here much more interesting as corollary of this one, because in the case of Haar function, the square function, non-classical Haar function and square function and classical are coincide. So you can just write this inequality with the same constant that we had in case of Rademacher functions. We also consider some super exponential inequalities using the method. We can also prove this inequality, where again dk is general martingale difference. Here we have the non-classical square function L-infinity norms, and here if you fix the lambda, this constant here, the sharp, and also it can be considered in the context of Orlich spaces with the Luxembourg norm. So you can write this inequality with a sharp constant, this, which is a generalization of some previous results, Grigori in 1996, where author consider xk was independent symmetric random variables. Okay, so here are some two problems that I couldn't solve it, and so this inequality we had for in the case of p greater than 3. So in this case, this inequality, I don't know whether it is. I think it should be true, but I don't know. And in case of fixed n, in case of fixed n, also the problem is find the value of this constant in case of Rademacher and Haar function in case of p is less than 3. That's all.